All right, slopes of implicit functions. Okay, so right before this, we talked about the difference between explicit and implicit. And if you remember, implicit functions have equations that have x and y on the same side or all intermixed together, while explicit have the y's and the x's separated on two different sides. Um, okay, so we're gonna delve into this new topic, implicit functions, and talk about the slopes of them. Okay, so right away, if we look at this implicit function that I gave you, this is the graph on to the right, and you'll notice that it's a nice circle. Um, Clearly, it doesn't pass the vertical line test, but there it is. It's still our beautiful circle. Um, and I'm going to tell you that the slope function is this. So please write this down. It's dy dx is equal to negative x plus 3 over y plus 2. Okay. Now, this is the first time you're seeing a derivative equation that has both x and y at the same time. That's a little strange. Um, and this might also be your first time really seeing dy dx as well. So I want to first talk about the derivative notation real quick before I continue. Okay, so what we're used to seeing is the first derivative, we might see it written in this notation or form, f prime of x, right? That's pretty straightforward. Or y prime, something like that. But today I'm also letting you know that another way to write it is dy dx. Okay. Now, calculus was created or invented by a couple people, and so depending on who kind of invented calculus, they wrote the derivative functions a little bit differently. So let me talk about this dy dx real quick. So the d here, if you what it basically means is a very small change. Okay, so what this dy dx is really saying is it's a very small change in y over a very small change in x, right? Now, remember, what is slope? Isn't slope just change in y over change in x, rise over run, right? But to find an instantaneous slope, we need a very small change in y over change in x, and that's what we call dy dx, okay? A very small change in y over change in x, okay? Now, it doesn't just have to be dy dx. Depending on what your variables are, it could even be something like dh dt. So for example, let's say I had a function, h of t, which might be my height or something like that, is equal to negative t squared plus 4t. And my height is affected by my time, t being time. Okay, then a couple ways we can write the derivative notation might be what you're familiar with, h prime of t. But we also learned that another way to say it is dh dt, because we're taking the change in height over the change in time. Okay, and if we take the derivative, it's just going to be negative 6t plus 4. Okay, so I'm just showing you that this is another way we're going to write the derivative. Okay, so going back here, I just gave you that the slope of this implicit function is right here that I'm giving you. Later in this unit, we're going to learn how to actually figure that out ourselves. Okay, but in the meantime, let's just work with that. So that's the slope equation. So that means that let's just look down here at the next directions. It says complete the table below, finding the value of dy dx, which is our slope, at each of the indicated points. Then draw the graphical representation, the tangent line on the graph at each indicated point. Okay, so let's just look at 0, 2 first. a quick second right here. Maybe I'll change the color. 0, 2. And I'll just kind of sketch my slope for now. I'm guessing that's maybe a slope of a little less than 1 about, but let's just see how this works, okay? So if I want to find the slope at 0, 2, I'm going to write dy dx, and what we can do is put a line and put the coordinate pair 0, 2. What this means is I'm finding the slope at this point, okay? So if I plug it in, I get negative comma plus negative something plus 3 and then something plus 2 according to my derivative over here, my slope given, okay? So if I plug 0 and 2 in, it's going to be 0 up here and 2 here, which is going to give me a slope of 3 over 4, which makes sense. This graphical representation looks like 3 over 4. Now maybe I could be a bit more accurate. So I'm going to go up 3, 1, 2, 3, over 4, 1, 2, 3, 4. And I can go down 3 and over 1, 2, 3, 4 this way. And we can see that this is the slope of the tangent line. Pretty neat, right? So it's really cool that we can have slopes that include both x and y terms at the same time. Really cool. Let's do one more example. Let's find the slope dy dx at 3 comma negative 7. Okay, so I know it's going to be negative 3 plus 3 over negative 7 plus 2. And we see here that that's going to be 0 over negative 5, which is just 0. And so at 3, negative 7, 3, negative 7, hey, that's pretty cool. I see that my slope is a flat horizontal line, and that makes total sense to me. Okay, so what I would like you to do is do the rest of these 4 slopes to practice.